Hey, welcome to our Unit 7, Day 9 review notes. So this is part 1. Part 2 will be with another teacher. So here's just like the basics of some of the stuff that we talked about in this unit. We've got our exponent rules listed again. We've got powers of 0, including negative exponents. So jumping on in here with our example of AR raised to the negative 2. That's the same thing as 1 over AR raised to the positive 2. So when it's a negative exponent, I just flip it to the other side of the fraction bar, and now it's positive. And I'm going to change this pen color. I don't love that. Let's do like this purplish blue color. All right, so this is 1 over a squared r squared with some distribution. And this guy, only the x is being raised to the negative 4, so only he's going to move to the other side of the fraction bar. In this example, they're going to flip-flop places. The 5's still going to stay, but the y squared is going to move to the top, as where the x to the 4th will move to the bottom. And then lastly, this, when you have a fraction raised to a negative exponent, I can flip the base entirely, and now it's a positive exponent. So that's the same thing as 9 over 4. So it's really important to note that negative exponents don't create negative numbers. They really just create reciprocals where things flip around. So these are some important notes that I would pay attention to. All right, power over root, I already had talked about in a previous video. So just remember that you can use that to rewrite fractional exponents as radicals and vice versa. Which then leads us into exponential functions. We talked about exponential growth, where it's rising from left to right, versus decay. And the way that you do this, or figure out whether it's growth versus decay, is by looking at the b value, which is the base of the exponent. So like in this first example here, I'm noticing that the base is 1.3, which is greater than 1. So that means this is exponential growth. As where our second example is 0.8, which is less than 1. So that would be exponential decay. Now with each exponential function, they always will have an asymptote, horizontal asymptote, at the x-axis. So it always starts at y equals 0 for your asymptote, and then it can shift up and down depending on the transformations that happen. So like when you guys look at this first example over here, let's start just by even talking about the transformations. I'm seeing a vertical stretch of 2. This x plus 1 means left 1, and the minus 5 means down 5. So this exponential growth function was shifted down 5 units. So if the asymptote's normally at y equals 0, now the asymptote would be at y equals negative 5 because of that downward shift. For the next example, I'm seeing 1, 2, 3 transformations, the first being a reflection in the x-axis. That's what that negative in front does. The x minus 3 means move to the right 3 units. And then the plus 4 means up 4. So now the asymptote would be at y equals 4. So whatever your shift up or down is going to correspond to the asymptote. Now in both of these cases, no matter what, the domain is always going to be all reals. The range, though, is dependent on the asymptote. So like this exponential growth function has an asymptote of negative 5. So that means the range would be negative 5 to infinity. As where with this one, our asymptote now is at 4, so our range would be 4. Actually, I take that back. This is a negative, so it's being flipped down. So this would actually be from negative infinity to 4. So just keep that in mind. As far as the percents of growth or decay, this one up here is growth by 30%, because if I subtract 1 from this, that leaves me with 0.3. So we are increasing by 30%. As for this one, if I subtract that from 1, that leaves me with 0.2. So you're actually decaying by 20%. So hopefully all that sounds familiar. Next little section here that we would have talked about in our Unit 7 is exponential regression. And just FYI, there actually are other regression types that you guys could use, like linear, quadratic, power. They're all listed under the same screen. So let me see if I can actually pull a calculator up here. Here's my little calculator emulator. I want to find an exponential equation that will model this data. So I'm going to call this L1 and this L2. And I'm going to go to my calculator and hit Stat and Edit. Okay, I'm going to type in this data now. Oops, sorry about that. Oops. Okay, so I'm hitting 2, enter, 4, 6, 8. Okay, and then I'm going to put my data over here. All right, so now that I've typed that in, I'm going to go back into Stat, Calc, and then I'm going to do an exponential regression, which is all the way down here at option 0, where I have my X and my Y list typed in for L1 and L2. So I'm just going to go ahead and calculate. And there you go. So Y equals A times B to the X. So rounded to the nearest hundredth, I would have Y equals 5.17 times 1.09 to the X. And that's my exponential regression equation. All right, coming over to logs. Okay, just some nice little rewriting facts here and some common and natural log facts to know. When we rewrite a log as an exponential, we use our lasso method. And then when we go in the opposite direction, so exponential to log, we use our BAP method, base answer power. Now, logs are the inverse of exponentials and vice versa. So if I want to find the inverse of this log right here, I would just switch X and Y. And then I'm solving for Y. So I'm going to isolate this log by adding the 3. Divide by 2. And then the base of a natural log is E, so I can lasso this. And that gives me Y. And then that's my inverse. So I just put my little inverse symbol there. Okay, same idea. Now this is an exponential, so I want to find the inverse of it. X equals 3 to the Y minus 5 plus 7. Isolate the exponential. And then BAP, so log base answer equals power. And then add the 5 over. So the inverse would be log base 3 of X minus 7 plus 5 by moving that 5 back over. And notice how the 5 doesn't combine with the minus 7. That's corresponding to a shift to the right 7 units. Now, if we want to graph a log, this is where these are keystrokes. So math alpha math, and that'll pull up your log base. Now, before I even get started here, I can tell you this is a log function that's been shifted to the right 2 units. Normally, logs have an asymptote at the y-axis, but if I shifted everything over 2 units, here's your asymptote at x equals 2. All right, let me pull my calculator back up. See if I can get these side by side here. If I go to y equals and type math alpha math, there's my log base, and I literally can just type in what I need. Now, a quick little graph will show you what it looks like, and then going to your table of values, you can see that first error at 2 because that's where the asymptote is. So I'm going to plot some nice points here. I've got 3, 0, so 1, 2, 3, 0, 5, 1, and then I think I have another one way out here at 11, 2. So 5, oops, that got ahead of me. 11, 2, yeah. 6, 7, 8, 9, 10, 11, 2, Now, a lot of the time students will leave their log function like that, but that looks like a square root function. Your log function approaches the asymptote, so don't forget the tail that extends downward. So you guys got to be smarter than your calculator there. All right, so the domain of a log function would be from -2 to infinity. Oops, keep writing that backwards today for some reason. -2 to infinity. The range is going to be all reals. You're forever going down and forever going up. And like we said, our asymptote's going to be at x equals 0. All right, last couple little things we got to talk about here. Just even evaluating logs. Whenever I do this, I'm thinking to myself, 6 to what power gives me 216? So 6 to the third power would give me 216. 4 to what power gives me 1? Well, anything to the 0 power gives me 1. 2 to what power gives me 16? Well, that would be the fourth power. So logs are really just exponents. So if you just pose it as a question to yourself like that, you should be able to easily evaluate those without using your calculator. So this is 3 minus 0 plus 4, which just goes to 7. Lastly here for this question, growth or decay and by what percent? Be careful, you have a negative x here, and that's important to note because at a quick glance, you might think it looks like this. And you would say exponential decay, but that's a negative x, okay? So that means this is y equals 2 to the 0.7, and I can bring that -1 inside using my exponent rules. And then if you actually type 0.7 to the -1 in your calculator, this is what you're going to get. So that base is clearly greater than 1. So because our base is greater than 1, that means this is exponential growth. And we are growing by, if I subtract 1, approximately 43% growth. Like 42.8. I don't have any rounding directions there. All right, so that concludes our video.